Hey class, Dr. Yeager here. We're going to continue on with chapter 11. We left off last time talking about mechanical weathering agents. Remember that mechanical weathering agents in terms of rocks are just mechanical forces that break rocks down into smaller pieces of the same rock. We don't change the type of rock in the weathering process. The second of those kinds of weathering that we talked about was called chemical weathering. And chemical weathering happens as rock is broken down into smaller materials through some sort of chemical process, some sort of change in the minerals through a chemical reaction. And this is really common. It's really common here in the hill country. It's, as we're going to see, in certain parts of the country, it's the predominant form of weathering, or at least equal to that of mechanical weathering. The most evident, I think, the most obvious form of chemical weathering that people are familiar with is that of oxidation. Oxidation, I'll move myself up here. Oxidation happens when you have a rock that has a mineral in it that's chemically reactive with oxygen, hence the name oxidation. For example, if we have a rock that has iron in it, and iron is highly reactive with oxygen. If you've ever seen an old car that's been sitting in a junkyard or sitting in someone's backyard for a long time, you know that the iron in that car, which can be found in the steel that used to be common in cars, not so much anymore. But the iron that was used to make the steel over time reacts with the oxygen in the atmosphere and oxygen in precipitation, and that creates a chemical reaction, which is known as oxidation right here. For practical purposes, what that means to us is that over time the iron reacts chemically, it turns into rust. That's why an old car that sits around and waiting around to be refurbished over the course of 20 or 30 years will turn into an old rust bucket. Well, rocks that have a lot of iron in them, particularly sandstone and rocks like that, that iron will react with oxygen in the atmosphere and oxygen in precipitation, and over time it turns rusty. It turns, excuse me, it turns this red, orange, rust color. And if you've ever been out in the Southwest, Arizona, New Mexico, Nevada, Utah, you know that this red color dominates the land, and that's because that iron in that rock has been affected by this oxidation process. That's rusted rock. Again, if you've ever been out there, you'll know that it's not uncommon to be able to take your hand on some of this rusted rock and sometimes just flake it off from the larger rock itself. Sort of just break little pieces off, because oxidized rock is considerably weaker after it's gone through this oxidation process. We don't see a lot of oxidation around here in San Antonio because we don't have a lot of rocks with iron in them. But that doesn't mean we don't have chemical weathering around here. We see a lot of what we call carbonation around here. And carbonation happens when you have a chemical reaction between carbon dioxide and particularly carbonate rocks. And carbonate rocks, such as limestone, are reactive with carbon dioxide. So whenever it rains, there's carbon dioxide in the rainwater, and the rock reacts chemically with that carbon dioxide. So whenever you have carbon dioxide in rainwater, it's naturally occurring, but it forms a very weak acid. It's called carbonic acid, and again, it's natural. Nothing to be worried about. It's not acid rain or anything like that. But when that carbonic acid comes into contact with limestone, there's a chemical reaction that produces this CaCO3. And for for purposes of this class and for purposes of your project where you're probably going to come into contact with limestone, you'll see evidence of carbonation all over the place. Whenever you see limestone that's been weathered down and has small holes in it, this is a particular kind of carbonation called honeycomb carbonation. You probably won't see anything like that around here, although you might, depending on where you go. Um, when you see limestone that's weathered down and has little holes in it, little marble-sized holes, those little marble-sized holes are evidence of carbonation. And around here in San Antonio, limestone makes up a lot of the buildings are made of limestone because limestone is really common around here. It's not uncommon at all to see older buildings that are 100 years old or so, where all of the blocks that at one point had nice sharp corners on them, when the building was first built, all those sharp corners are wore away, and that's because over time limestone just dissolves away as it comes into contact with this carbonic acid in the rain. If you ever go down to any of the Missions, the Alamo, those old buildings, you won't find any 90-degree corners on any of those buildings. Why? Because over the course of a couple centuries, those old buildings and those old right angles have turned into those 90-degree angles have turned into nice rounded edges as the limestone just wears away and wears away. So finally, other than mechanical weathering and chemical weathering, the last type of weathering I want to talk about is what's called biological weathering. And biological weathering is simply the wearing down of rocks based on something biological, meaning either a plant or an animal. It's easy to see and find examples of plants breaking down rocks. All you have to do is go out into the woods and you'll see plant roots tearing rocks apart. That's really, really common. But there are lots of other plants other than trees that that impact rocks in one way or another. We've all seen rocks that have moss or lichen on them. Lichen are actually small single cell animals that feed off of rocks through a process called ion exchange. And as they feed off the rock, they die. And then as they die, the outer layer of rock flakes off. So they're breaking the rock down into smaller and smaller pieces as they go. Trees are obviously the biggest factor in biological weathering, but these other types of plants can also have an impact. A much lesser impact would be the role of animals in breaking rocks down. So that would be something like mice and rats and squirrels getting into little nooks and crannies in rock and then burrowing as they move in and out, scratching the rock down over time. It's going to break the rock down very, very slowly. It's obviously a much less magnitude than the impact of plants, in particular tree roots. But altogether, biological weathering is an important part of weathering. Certainly not as important as mechanical or chemical weathering. And then just when we think about where weathering happens, obviously weathering happens all over the planet, but we want to make sure we understand the correlation between the amount of weathering that happens in a place and the climate or the weather of a place. Weathering needs two things to happen really, really quickly. It needs warm weather, and it needs lots of precipitation. It needs lots of precipitation because if you remember from chemistry class, water is a catalyst. It can speed up some of those chemical weathering process. Heat is also a catalyst. So that would also speed up some of those chemical weathering processes. And then if you, in addition to having warm temperatures, excuse me, warm temperatures, plenty of precipitation, but then you also have large diurnal, meaning daily temperature variations. So if it's warm during the day, it gets down to cold temperatures at night, and so you get that freeze thaw action of mechanical weathering, and then you also get lots of precipitation. Those are going to be the places where you have lots and lots of weathering. So those could be places like mid-latitude climates, any warmer places. You're not going to see nearly as much weathering in places that are cold and dry. So places like Greenland, places any E climate type or any D climate type, you're not going to see nearly as much weathering as you would see in a C or an A climate type. You would see weathering in B climate types because of the warm temperatures and the diurnal temperature changes. But you, since B climate types by their very nature are dry, you're not going to see as much chemical weathering in those places as you would in places that have plenty of precipitation. Okay, so the last thing we want to talk about in chapter 11 is what happens after weathering. Right? Remember at the very beginning of this, we said that weathering we talked about erosion, right? That's how we just conceptualize this whole concept of how the surface breaks down. And we said that erosion was actually just one part of this denudation process. That's actually the last part. We won't even talk about it until we get to chapter 13. So weathering is the first part of that process. Remember, that's where big rocks get broken down into smaller rocks. And then you have these broken down rocks that are just sitting there. Well, eventually something happens that causes those things to move. And it's that first movement, which is almost always caused by gravity, that we call mass wasting. Mass wasting is the process where something that has been weathered gets moved down, usually just a small distance. It's not getting carried away all the way out to sea or anything like that. It's not getting carried a long distance. That's what we would call erosion. It's just maybe rolling down a hill, or maybe just falling down, an escarpment, 15, 20, feet, a short distance. But it's that initial movement process that makes erosion possible later on. So this is what we call mass wasting. And as we're going to see, there's several different kinds of mass wasting we want to talk about. Mass wasting is caused by gravity. And so that's kind of getting probably to be a broken record at this point. Gravity is really, really important in this. So what are the things that are going to impact mass wasting as we go through these? Excuse me. One is called the angle of repose, and the angle of repose is an important concept. The angle of repose is a hypothetical angle at which any different surface can be at rest. If you've ever worked in the construction field or something like that, you know that the angle of repose is important because different piles of different things can stack up at different angles. And if you try to stack something up at an angle beyond its angle of repose, it's going to collapse down. You sort of already know this. Think about what you can. If you went to the beach and you're going to make a sand castle, and you had sand that was perfectly dry, and I gave you a bucket and I said, okay, go make me a sand castle, and you went and you tried to stack up your perfectly dry sand. Excuse me. You wouldn't be able to stack up your dry sand very steeply. That's because the angle of repose, the angle at which dry sand will stack up, isn't very steep. It's only going to stack up at a relatively low angle. If we added a little bit of water, just a little bit of water to your dry sand, we would find that it would stack up much, much more steeply. Right? We could stack it up much greater. And if you've ever built a sandcastle, you know that's what you want. You want sand with some water in it, but it can't be too dry. Now, if we added a ton of water to your sand, and essentially now you're just dealing with this sloppy mess, again, that won't stack up very high. Different things have different angle of repose, and if we are dealing with soil that's a certain material, that's going to be important for us to know in terms of mass wasting. We're going to stop right there. We'll finish up chapter 12 here in just a moment.